Today we're going to talk about a new toy I got in the mail this week. Oh, and that notice down there in the corner that says includes paid promotion? Yeah, we're going to talk about that. Welcome back to Cloud 42. I'm James. Whenever you're working on an embedded system like the electronic Leadscrew, debugging can be a challenge, and one of the tools that's very useful in that process is a logic analyzer. You can think of a logic analyzer like an oscilloscope, but instead of being focused on capturing analog signals, it's focused on capturing a large number of digital signals and then doing timing analysis, protocol decoding, and other kinds of useful operations on that data so that you can get an idea of what's happening in the hardware. This is the logic analyzer that I have been using on this project so far. This is an old Agilent 16702B, and by all modern standards, this thing is a dinosaur. This one dates from the late 90s. In fact, it has embedded Netscape Navigator in it, which is basically useless because it doesn't support any of the encryption protocols that are in use today, and it often tries to phone home and for some reason can't find Netscape's website. Anyway, this machine is pretty much loaded. It's got a whole bunch of probes. It's easy to set these things up with 100 or more digital channels. So you've got pods and connections to hook into your circuit. This one's even got the 4 gigahertz modules, and I think a couple or 2 or 4 analog oscilloscope channels as well. And so it's a very capable machine, but it's slow, it is big, it is heavy, and it is loud. This thing has a lot of hardware that was super high tech in its day and very power hungry, generates a lot of heat, so the fans generate a lot of noise. And besides just the fact that this thing takes up all of the space, the working space that I have here in the shop, and I don't have a bench deep enough to put this on and actually still have any room to work, I do occasionally shoot video, and the noise that this thing makes is really difficult to work around. So I wanted to get something better, at least something that's a little bit better suited for the kind of stuff that I do. So I've been thinking for a long time about picking up a Saleae Logic Pro 16. I've been reading about them, I've been kind of looking at them, and it looks like it's a pretty good match for my project here. It will run at 500 megasamples per second, so it'll easily handle 100 megahertz signals, and that's pretty much what we've got on the board. The clock rate on this microcontroller is 100 megahertz, so everything will be slower than that. That's also a good match for like ESP8266, and it's plenty for dealing with anything you can do with most Arduino platforms. But of course, they don't give them away for free. But it doesn't hurt to ask, right? So a couple of weeks ago, I sent an email to Saleae and offered them the opportunity to sponsor the electronic Leadscrew project by donating a logic analyzer. And while they told me they couldn't donate one directly, they did send me a coupon for a substantial discount. And I, not being an idiot, ordered one immediately, and it arrived this week. So let me get this stuff all cleared out of the way and make some room, and we'll set this up. But if you're worried about shill videos, I guess this is kind of a shill video, so don't watch it if that bothers you. Anyway, let me get some stuff cleared off of the bench here, and let's open this up and see what we've got. So technically this isn't an unboxing video because I've already unboxed it, but I thought it was interesting some of the details about how this was packaged, so I thought I would go ahead and put it back in here and show you anyway. So the first thing you're greeted with when you open the outer packaging is this nice slick matte black box, and this kind of reminds me of Apple packaging. And the only reason I mention this is, not to be a fanboy, but I actually think it's kind of interesting when companies do this. I've seen a couple of Kickstarters recently that have done a really great job with packaging. Obviously, Apple does a beautiful job with packaging. But why would you do this? Why would you spend the money to do something like this? It really all just comes down to psychology. This does not make the product any better. This does cost money, but it doesn't make the product any better. All it does is it creates an experience when you open the box. And that experience gives you an impression, false or otherwise, or justified, that this is a quality product, and it creates goodwill and automatically biases you towards assuming that it's a good product. And so if you have an amazing experience when you open the box, or a pleasant surprise experience because of quality packaging and style in something like this, it predisposes you to positively view the product. So then later on down the road, when you have the inevitable frustrations with any new product, you start from the assumption of, oh, this is a really quality product, so the problem must be on my end, and you're going to be willing to forgive more of that. It's just human nature. So inside we've got a nice little carry case. I don't care about this. The product itself is so much smaller than this case. This is just going to take up space. It's going to protect it. It's going to keep everything together. That's great. But I have these things laying around everywhere. Here's one that came with my GoPro cameras. I don't use these. If I took every camera and had it all nice, neat in a little case like this, they'd take up 3 times as much space as just throwing the camera in a toolbox drawer. This one, if I don't use it all the time, this might be handy. I mean, it's a nice touch. And inside we've got the logic analyzer itself, and these things are very, very nice. It's a machined aluminum case, which is totally not necessary for this. Plated plastic would work fine, but it's heavier than you would expect, which again gives you a positive psychological response to the product. And with the rubber feet on there, that's going to actually, that stays put pretty well. So that's a nice touch. Got the inputs here, USB, and you can see that is USB 3 with the additional power pins. So this is powered just from the USB port. Underneath here we've got the terminal wires for connecting it to your circuit. And this is just a 0.1 inch header, and each one of these has got 4 signal wires and 4 grounds. And they're nice enough. Heat shrink and labeled heat shrink on the end. So these are just pins. You can stick these onto header pins, which is the way we're going to use it. This unit also comes with these little grabber clips. And I don't know if you're going to be able to see anything here, but they have little tiny pins on the end, little tiny hooks on the end, so you can clip these onto your circuit. This is actually kind of nice. They come in a little plastic case. This is kind of another case of, packaging overkill. It's nice. Do I like this? I don't know. Maybe. I think I probably like this just because the tips of these things are pretty delicate and they are pretty easy to break. For my other logic analyzer, I've got a few dozen of these, and they're just in little plastic bags, and that works just fine. But they do get broken. I have broken a few. I guess that's kind of nice. It kind of continues the theme of the ultra premium packaging and making you feel good about the product. Does any of this make the product actually better? No, not at all. What really matters to me is the performance of it in terms of the electrical signals and the capture speed and noise and things that will make it useful or not useful to me. All this stuff, I guess, is nice, and I guess it will bias me towards feeling like it's a good product. But honestly, the thing that biases me the most towards assuming that it's a good product is I spent a bunch of time researching it and then went out and got one. Yeah, they cut me a deal on it. I probably would have paid full price anyway. And now, having spent my money, I have this thing in my hand. I want to be right. I don't want to discover that I made a mistake. That's probably the thing that biases me the most. It comes with the USB cable. That's actually fairly heavy, which, okay, I can understand. It is high speed. You want a quality cable, but I'd rather have something thinner and lighter. I don't eat a lot of ramen. It doesn't really fit my macros, so I don't need that. Okay, this is hilarious. Okay, the quick start guide. 1, software. 2, wire harness. 3, USB cable. 4, collect data. That's great. Okay, well, let's hook this thing up and give it a try. See what it can do. I have already downloaded and installed the software, and this is it, Logic 2, and I went ahead and downloaded the test version, not the standard stable version. So if I run into any problems, I'll back up, but I wanted to try the newest stuff. See, we can select which logic analyzer. I've got the Logic Pro 16, though I don't have it connected right now, and you can see the warnings here saying there's no connected device, demo data will be generated on capture. If I click the capture button, looks like it's generating demo data, and we can zoom in here, and we've got a couple of digital channels and a couple of analog channels. Okay, let's hook up the actual logic analyzer here. Get this extra cable out of my way. Okay, connecting, and just saw it run up a percentage, and so I assume that what it was doing was downloading the software into the FPGA in here. We've got a light on, and if I go back in here now, Demo Logic Pro 16, disconnected, please create a new session. Okay. There's a new tab, it says Logic Pro 16, okay, and if I click Start, it's capturing, and of course there's no data there to capture. Okay, well let's plug in some wires here. And I've got a little cheat sheet of which channels are which. So my clock I want on input 0, so I'll just go ahead and hook these up. Let's see, that's input 0. Let's put that on the clock pin. Pin 1 should go on meso. Ten to the encoder 1, encoder A, and 11 to the encoder B. Okay, I think that's everything connected. Let me grab a power supply and turn this on. And I see some activity on the display, which means that it is running. And let's just start a capture without doing any setup. We've got channel 0 and 1 connected. They should have some data on them. Okay, and I'll just stop that. And let's zoom out here, find something. Oh, yeah, look at that. Got some actual data on those channels. Okay, good. Now that we know we've got that, let's go ahead and set this up. Come over here to capture settings, and I know I want on the digital, I want the first 11. I want to capture as fast as I can. Let me turn these off. What's the fast? So I can go 250 megasamples per second, and I am using 3.3 volt logic. Let's do a quick capture here and make sure we're getting stuff on all the pins, and it looks like we are. Okay, let's label some of these things. Encoder 1A, I recognize these ones down here. Encoder 1B, and start with the top. Channel 0, got my display here. Let me just go ahead and set all these. You don't need to watch this. And I will come back when I have these set up. Okay, there I've got everything set up. Let me just run a little bit longer capture here. You can see down here it's showing the memory that's being used, and 5 megabytes. Oh, this is great. Okay, so it's going to have plenty of room. Okay, let's stop that. And let's see, what can we see in here? So what we're looking at here is the SPI clock. So there's the clock signal for communication with the control panel display. So every byte gets 8 pulses on the clock. The meso pin isn't used here because it's bidirectional. So here's MOSI. This is the actual data. So this is data being clocked out. I happen to know that this region right here is where the key presses get read. And then here's the display data being clocked out further. Here's the display chip select. So this goes low, we clock out 1 byte, goes low, we clock out 1, 2, 3, 4, 5 bytes. Goes low again, there's a byte, low, a byte, and then low, and then here's all the display data being clocked out. So this is working great. Let's see, so what's the width here? Oh, that's cool. You can just highlight over it and you can see the pulse width. So that's 5.12 microseconds. And then it shows you the full wavelength is 10.24 microseconds. So 10.24, 10 microseconds would be around 100 kilohertz, which is exactly what I think it's running at. Should be about 97. So I see here that that's 10.24, a little more than 10 microseconds. That totally makes sense. So that's the clock there. Then down here below, let's see, can I change the view to get all these on the screen? Decrease size. Yeah, there we go. Okay, there. So now I've got everything on the screen. So down here at the bottom is my encoder 1A and 1B. So this is the quadrature encoder input. And if we zoom in and look at that, yep, that looks like a nice quadrature signal. In this case, it's being generated by this little microcontroller. I've got a little Arduino here that's generating it. So that totally makes sense. These next two are the Debug ISR and Debug UI. These are logic outputs that show the activity in the main interrupt service routine and then on the UI service routine. So this one, Debug ISR, this is the time that's being spent in the actual interrupt routine that is updating and potentially generating pulses out to the stepper controller. And that looks like 1.4 microseconds. On my other logic analyzer, I was reading 1.3. So there's 1.328. Yeah, so that totally makes sense. 1.412, 1.332 microseconds, great. And then it's actually running every 5 microseconds. So yeah, that totally makes sense. That looks good. And if we zoom out here further, then we should be able to see the pulses. Here's the large pulse on the Debug UI, and that's running about 2.6 milliseconds. And that's how long it takes to run the routine that actually deals with the display. And here's the clock and everything that's going on up here. So I think, so there's one pulse, and so I can see that, and then I can scroll horizontally, or there's a little button I noticed here that says next edge. So if I click that, yep, it scrolls over and finds me the next edge on that pin. So I can go from one execution of the display loop to the next. Oh, we're at the end of the capture, so I can go back. That's cool. Okay, so I can move through and find that. Same thing up here. So here are the steps that are being generated. And you can see there are, so if I look between steps, that's 486 microseconds. And if I go ahead and dial the feed rate up, okay, that's 486 microseconds. Let's run this again. And now I check the time between, and it's only 125 microseconds. Great, so I can get good measurements on that. That's cool. So I have to say that the software is totally what makes this thing work, right? If you look at the $1,000 price tag on this thing and you open it up and look at what's in here, yeah, there's a Xilinx FPGA in there that's a fairly expensive part, but I mean, we're talking tens of dollars kind of part. We're not talking about $1,000 worth of hardware in this thing. But what really makes something like this worthwhile is this software. And I have to say, having used this just briefly, I've just barely scratched the surface on this thing. This is way better than that Agilent logic analyzer. Besides the fact that this thing is responding rapidly because I've got it running on a modern computer, just simple things like, hey, go to the next pulse, or you just hover over the thing and it gives you the timing. This is great. I mean, this is stuff that Agilent logic analyzer might be able to do, but the user interface on this, because it is modern software, is way, way easier to use. And I love this being able to just search through and find the next invocation of something. Let's try something here. So we can see here's the display being clocked in, and we can see the actual data here, and there's this big blank area here. Let me hold down a button and do another capture, and we should see some pulses in this area. So let's capture, stop, that should be plenty. And let's just go find the next pulse. And there it is. That pulse right there is the button that I had pressed. And if I do another capture without holding a button, that should not be there. And sure enough, there's no data in there. That's cool. I like that. So we've got all this SPI data up here. Let's see if we can add an analyzer to that. So analyzer, SPI. Okay. So Mosey is the O2 Mosey, Meso, it found it, clock is clock, enable is the display chip select, great. Significant bit, most significant bit first. Now that's normal. I happen to know that this particular display module uses least significant bit. 8 bits, clock low when inactive. I think the clock is high when inactive. Data valid is on clock leading edge. Let's try that. The labeled line is active low. Okay. Let's try that. Oh, and it went back and analyzed this. Let's see what we've got. 0x40, yeah, that's correct. Let me make this bigger so you can see it. There we go. And I'll shrink this vertically a little bit. And oh, look, we've actually got data here. Oh, and there's the data from the analysis. Okay, that's pretty neat. Let me turn this off and make a little bit more room here. And it looks like we're showing the data, and I recognize that 0x40, 0, 0, 1, and so we've got zeros all the way across here, though I think this should be 4 zeros because that's the button, so maybe we don't have the analyzer set up right. Let's clock is low when inactive and see what that does. Oh, that doesn't make sense. Okay. High when inactive, data is clock. Let's say trailing edge, see if that gives us what we expected. There we go, that's right. 0x40, 0x42, this is the 1, 2, 3, 4. Yeah, this is exactly right. So this is the display brightness. This is the bit, or the, is that, do I have that right? Nope, that's not right. So this is the command to set incremental mode, I think, and this is the command to tell it to read back the buttons. And then here are the 4 button values, 0, 0, 0, 0. And it's, let me rerun this with a button pressed so we can look at that. And there it is, 0, 0, 10, 0. So 0, 0, 10, 0, yep, so there is the button press in there. So we can actually see the data, and we can see the data all read out here. Well, that was pretty painless. I'm actually really impressed with that. Yeah, so it's showing the clock up here, and it's showing the little arrow for the leading edge, or I guess it's the trailing edge, because the clock is active, inactive high, so it's active low, and then it's the trailing edge, which would be the high rising signal. I knew it was triggered on the rising edge, I just wasn't sure what they were going to call that. So that's the correct configuration for this setup, and look at that, we can actually see that happening. That's pretty cool. I've set this up on my, I've set up the decoding for SPI on my oscilloscope before, and it was not nearly this easy, so that's pretty cool. So far, so good. And like I said, it's not the hardware that makes this thing amazing. The hardware is just necessary. What actually makes something like this really useful is the software. And so far, gotta say, I'm impressed. Okay, so we're capturing data. We have got the decoder going. Let's try playing around with the analog. So let's go back over here and let's see, that's the clock. Meso's got nothing, it's Mosey. So let's turn on analog capture for Mosey and the clock. And so we're running 125 megasamples per second, so that just got turned down because I enabled the analog channels. So 125, 50, let's give that a shot and see what we get. Yeah, so the data is climbing very rapidly, 5, 6, 7, 800 megabytes. Let me stop that. And let's see what we've got down here. So there's clock and Mosey. Let's actually go someplace where we've got data. Oh, there's some data right there. Okay, let me move this clock up, the analog clock. Let's move this up next to the digital clock. Okay, that was exactly how I expected that to work. And let's bring the analog Mosey signal up next to the Mosey signal here. Okay, and let's zoom in and see what we've got. Let's look at this. Let's look at the Mosey signal. Let's just look at one of these edge transitions. Okay. Well, I don't know what I expected to see, but that actually looks just about like what I would expect. This goes high, and at right about that time, oh, that's cool. It shows the voltages when you hover. That's pretty slick. Okay, so 1.463, that makes sense. That's right about the position where this thing timed and registered it as high, but you can see on the analog signal that instead of just snapping high, it actually get a slower rise. Now, this ringing at this frequency, I don't think that's actually there. I think that is just the interpolation of the individual samples because we're not sampling that fast. So an edge this quickly is just going to show that. I mean, that's being drawn, but at least you are seeing that there is some rise time there. So I think, oh yeah, and here's the clock. If we look up here at the clock value, same thing. It doesn't go down suddenly, it falls off. But you can see that it has gotten clear to the low value relatively quickly relative to the width of the actual clock pulse. So we can see here that we are keeping up just fine. Where if the, because of the capacitance on the line, this thing were dropping much more slowly, we would see a much slower ramp down. So I can look at this and this isn't, this isn't what I would see with a real fast oscilloscope, but I think this is pretty useful. I can at least see that the line is getting low fast enough that it's, relative to the width of the pulse, I don't have a problem here. Now, I don't have a system I can plug into that is running really slow right now, so I don't have a good way to to look at what it actually generates on a real slow signal, but that looks all right to me. Let's go down and see, since we reduced the sample rate, how wide are we actually measuring these pulses. These steps should be 5 microseconds, 4.848. Yep, I think they are accurately pretty close to 5, so that would just be error because we've reduced the sample rate. Still, that's not bad. And then let's go down and look at the Debug ISR. 1.4, I know this takes about 1.3 microseconds, so that actually still looks pretty good. What happens when we reduce the sample rate even further? Let's take it down to 50 megasamples per second. Just run a quick test. 1.3, 1.4, 1.3. That's still plenty fast to catch that. What if we go even lower? 25. .4, 1.3. Yeah, that still looks nice and consistent. I'm not seeing big aliasing issues. Well, I gotta say, I was pretty concerned that this was not going to work out. You know, I mean, I've seen, you know, there's a lot of USB logic analyzers out there, and you know, there's a lot of junk, and I really wasn't sure. I mean, I knew the Saleae product was supposed to be a premium product. I mean, obviously, you look at the price, and you can see they positioned it as a premium product, but honestly, this has exceeded my expectations. I was expecting it to be just kind of barely good enough, and you know, if I really had something serious, I was going to want to pull out the Agilent, but I can't find any problems with this. This seems to be working okay. I did see a couple of errors when I first powered it on around some extensions that were not loading properly, and I don't know if that's just because I'm using the bleeding edge software and not the main stable release branch, but I don't know, time will tell. But so far, let's see, they've got all kinds of plugins here. So you've got extensions. You can, apparently you can write your own extensions in Python and plug these things in. I haven't even looked at it, so don't quote me on that. I'm just looking at stuff that's in here. Duty cycle, gyros, I2C, featherwing stuff, peak-to-peak voltage, pulse count, SPI flash. Oh, that's cool. So there's SPI flash. I do have an SPI flash on here that I will eventually be playing with. So we'll have to see, annotate common SPI flash commands. And that looks like that's an Adafruit add-in. Well, that's pretty cool. Well, I will have to play with this stuff and we'll see how this goes. But so far, looks like money well spent. So, you know, take that for what it's worth. Ultimately, I am not doing a review of this product or recommending this product, but it does seem to be a pretty good fit for what I'm doing, and it's giving me the data that I need, and more importantly, I don't have that huge thing on my desk that I have to deal with. Plus, I can get good solid screen captures because I'm running on a real computer. So, for what it's worth, yeah, I'd recommend picking one of these things up. I'm pretty happy with it. Well, that's all that I have for you today. If you're enjoying these videos, please give me a thumbs up. Feel free to subscribe to the channel and leave me a comment. I'd like to know what you think. If you've got experience with these logic analyzers, go ahead and throw that down in the comment. If you love them or hate them, let us all know, and more importantly, let us know why, because I'm curious to see what other people's experiences have been. Thank you for watching.